Thank you all for coming out. Today I will be presenting on distributed memory parallel JointNMF. I'd like to start off by thanking my co-authors, Srinivas Eswar, Koki Hidashi, Ramakrishnan Khan, Gray Ballard, Richard Vudick, and Houston Park. This work was a joint collaboration between Wake Forest University and Georgia Institute of Technology, and it was done in collaboration with Oak Ridge and Oregon National Labs. The work was funded by a NSF grant. So let's get started. So start with the long story short, our contribution is the first distributed algorithms for JointNMF. So that raises the question, what is JointNMF? JointNMF is a matrix clearing approximation technique for analyzing attributed graphs. So if you recall, attributed graphs generally consist of a series of a graph network, so it consists of a series of nodes and edges, wherein each node has a series of features or attributes. So here, for example, we have a citation network. Each vertex represents a paper, and the edges between papers represent a citation relationship. So in this case, we can represent each paper as a series of words that constitute that paper. So here, for example, all the words are corpus. It's byte, tree, atom. We see different word counts for each of the papers, and then of course the citation relationships between these four papers in our small example. Now we can take each of the vectors for the features corresponding to each paper, and use it to form the columns of matrix X here, and then we can use the edges to form a symmetric adjacent matrix S here. Now, what JointNMF does is it takes a attributed graph, like in our previous slide, and takes the result that forms X and S, the two matrices corresponding to the nodes and edge sets, and factorizes the corresponding matrices into two-factor matrices, here denoted W and H, where X is the product of W and H is the shared factor, and S is approximated by H, where thus H is a shared factor between the two factorizations. So JointNMF is a powerful tool for unsupervised analysis of attributed graphs, and in this work we present the first set of distributed algorithms for JointNMF. So let's go through and quickly go through the brief description of the contributions, and then we're diving into the actual algorithms that constitute it. So first set of distributed algorithms. So we have three different algorithms. The first is a distributed implementation of an existing sequential alternating nonnegative least squares based algorithm. The second is a proposed distributed algorithm based upon projected gradient descent, and the third is a algorithm based upon projected Gauss-Newton gradient. We then take these three methods and demonstrate their scalability on a large paper corpus consisting of 1,300 terms, 30 million documents, with around 1 billion citation relationships, forming this data set here. So here X is 1,300 by 38 million, and has around 1.3 billion on zeros. And the symmetric S matrix, it's around 38 million by 38 million, and has around 1 billion on zeros. So on this data set, we will show that the previous existing sequential MATLAB implementation took around 1 day. This data set our implementation on a single core took around 3 hours, and then on 48 cores we are down to 5 minutes. So let's quickly go over some of the more technical details of the JointNMF formulation. So specifically, JointNMF seeks to optimize this objective function, where we have our data matrix X and S, and then our factors W and H, where W and H are both non-negative. So the reason why this is useful is H and W are limit embeddings, which can be useful for identifying things like topics, clustering, so on and so forth. And on the last slide, we will show how you can take these factors and extract useful information out of the data set from them. And the non-negative factorization helps aid interpretability of the result. So let's go through and go through a brief high-level overview of the algorithms W that was for JointNMF. So the first is the Alternating Nonnegative Least Squares algorithm. It's based on a block-borne descent optimization method, and essentially, in essence, it alternately holds all but one factor constant and then solves for that factor, and then iterates the factors, and then iterates until convergence. And so this, previous to this work, this was the existing sequential scalar algorithm. It's only algorithm for JointNMF. The next algorithm that we propose is the projected gradient descent algorithm. Pretty straightforward first-order direct observation method. In essence, create the gradient of the trig function, line search for settlements, then follow with momentum, repeat until convergence. So this is one of the ones that you're proposing. And then finally, the third method is a projected Gauss-Newton conjugate gradient method. Second-order direct observation method. Brief high-level overview, basically create the gradient, and then approximation. Divide rows into active and passive sets. Solve for the step direction via the conjugate method. Then line search for step length, and then repeat until convergence. So this type method had previously used to compute symmetric matrix factorization, which is a subset of JointNMF. And so in this work, we proposed a modified version to handle JointNMF formulation, just basically adding an additional X matrix. So let's quickly go over a little more detailed explanation of the ANLS-based algorithm, and then in the interest of time, we'll just in the interest of time. So for the ANLS-based algorithm, we take the original objective function and we relax it a bit. Basically, we remove the strict symmetry constraint on S here by introducing this H hat variable, and then we incentivize H hat and H to be similar by this regularization variable here. Basically, the higher the beta value, the more similar H hat and H will end up being. And so essentially what I'm going to do is first we're going to hold everything but W constant, solve for W. Let's see here. You can see here that only part of the modified formulation is that equals W is this part. We will then repeat the same thing for H hat and the same thing for H. So at each step, we will work with the set of normal equations, which requires us to create a series of Gaussian matrices, which requires, in the case of H, this set of computations, and similarly for H, and a similar step for H. Now, so we're going to try to take our previous slide and scale it up into distributed dimensions. So just to reiterate, all these different interfaces previous to this for shared memory. This greatly contributes to data sets and feasibly analyzed by JointNMF, and we develop distributed variants of ANLS, PG, and PG&C items to get this. All the items that we're going to go over are live within the Planck framework to the following link. So let's quickly dive into one of the first set of challenges that we have to tackle before we can make distributed variants of these algorithms. So the first is figuring out how we're going to distribute our data over our processor data. So here we have 60 processors arrayed in a 2D processor grid, 8x2, and we have our X and S matrices along with the corresponding factors that we're going to be refining as we go on the algorithm. So first what we're going to do is we're going to take X and we're going to divide it up over the 2D processor grid, and then we will do the same thing for W, except for instead of doing it in 2D fashion, we'll do it in a 1D fashion. So if you notice here, we have W1, W2, W3, W4, distributed in a row-wise fashion across the 2D processor grid. We'll then repeat a similar process for H, except for instead of going row-wise here, we'll be going column-wise. And then S, we could also then 2D partition over the same processor grid. However, let's note a quick problem that we may encounter here is that you notice the size of X and S are significantly different. X appears to be much better suited to the two-processor grid configuration that we have here than S, which is least square. And so to fix this, we're actually going to show how we can have two custom processor grids, each for X and S. So instead of one 2D processor, we're going to have 2D processor grids, each for X and S, which we're going to do logically. Basically, in both processor grids, the basic concept is the same processors, it's just your logic can do 2D processor grids. So in this case, we'll have X distributed as previously, same with W, same with H, except for here, S is logically viewed as on a least square processor grid, which has a better aspect ratio for its dimensions. So in this case, we will have to duplicate the H matrix on this S processor grid, as seen by the see here, the red rectangles in each distributed column-wise. And similarly, if you call from the previous formulation, we also have our H hat variable, which only interacts with S, and so we can just keep it on S grid, just these blue rectangles here in each grid. Now, the reason why I do this is that this actually decreases the word communicated by up to a factor of square root 2. So it does save us a significant amount of communication overhead. One caveat is that it will require us to sync between the two grids periodically over the course of the computation, but that ends up being negligible compared to the overall. Let's scale that around. So now let's quickly go over some of the computational bottlenecks that all three algorithms encounter. So the first computational bottleneck that we encounter is the Gram matrix computation. In this case, it takes the form of W times W, or H times H transpose, as well as matrix multiply, which takes the form of X times H, W times H, and H times S. So extreme variants of these kernels are where we gain most of our performance improvements, and these specific kernels are already implemented within the upplane framework. So we leverage these limitations to facilitate our free distributed algorithms. So let's quickly go over these two kernels, just so you get a feel for how what really forms the where we get most of our performance improvement. It's the basis for the free distributed algorithms. So the first is the Gram kernel. So here we have matrix X distributed as previous, and a 2D distribution, and we have both H distributed column-wise in 1D fashion and W row-wise distributed in 1D fashion. So first, we're going to do a local matrix multiplication each processor, and then we will simply reduce all of the matrices together. And at the end of this, we will end up with the Gram matrix redundantly stored across the entire processor grid. So moving on to the matrix multiplication, we will begin by all gathering W over the rows. The entirety of W is redundantly stored across each column of the 2D processor grid. We will then do a local matrix multiply with the gathered onto W, and then we will do a reduced scatter over the columns. Now, one that's worth noting is now the distribution of the product is now column-wise. W was originally row-wise, and now the result is column-wise, and now the distribution matches H, which is what we want. As each processor locally has the products that it needs in order to compute its local updates. So, as a quick review of the now here we have some of a very high overview of the core computations of each of the three algorithms. So, Alternating Squares requires 1 W gram and 3 H grams, 2 S mults, and 2 eximals and 2 decimals, and similarly, slight variations for PG, PG, and CG. And here we have a table with some of the computational communication complexities for the 3 algorithms, and the majority of differences between these 3 comes from the differences in number of kernels for each of these. So now let's quickly dive into some experiments where you can see kind of where we can compare the scalability differences between the 3 algorithms. So quick experiment setup. All experiments run on a sugar cluster at there's an Institute of Technology, where there are 24 intercores per node, between 192 and 768 gigabytes of RAM per node. Here's some brief review of the density and sparse scaling parameters that we ran with. The base thing is the different ratios between number of rows and number of columns between the dense and sparse. And unless otherwise stated, the number of rows in each of the factories is 50. So we first, before we did any scaling experiments, we did some convergence studies between 3 algorithms that empirically demonstrate some of their respective conversion properties. So in this case, we have m equals 1,000, n equals 600, and k equals 30. So these are the sequential mathematications that we ran with before implementing the distributed variance. And from this, we can see that both PG and PDC quickly converge to a solution, whilst the PG and CG obtains a simply better solution than PG overall, while the least squares based method eventually reaches the best overall solution. And from this, we glean that if you quickly want like a pretty good solution, one might opt for the PG and CG algorithm. Whereas if one wants the best overall solution, it can be kind of tossed between PG and CG and ANLS. Now let's quickly look at some of the scaling results between the 3 algorithms. So we ran on the dense and sparse problem sizes up to 960 cores, demonstrating good scalability for all 3 methods. It's worth noting that in the beginning, with fewer core counts, it's mostly computational cost performance with the bulk of the time. But then as we scale up to higher core counts, the communication will perfectly take more toll. So let's quickly next go over some of the computation versus communication trade-offs for different grid sizes. So in this case, the sparse input aspect ratio was 4, so basically there was 4 times as many rows as columns. And as we can see here, the minimum running time is when the size of the processor matches, the shape of the processor matches that of the problem size. So here, the aspect ratio between rows and columns was 4, and we see our minimum communication time at the number of processors in the rows is 64, and then 16 processors in the column, and there's also a ratio of 4, and same for the computation, which is what we would expect. Now let's quickly go on to some of the real world experiments that I mentioned at the beginning of the talk. So here we have our data set with 1,300 journals, 38 million papers with 139 billion non-zero matrix, and then 38 million symmetric citation connection matrix with 1 billion non-zeros. This is from a subset of the measure of open academic graph. Where X is a term back matrix, this is citation matrix. Here we set K to 16, basically 16 columns / rows in the factor matrices. And we set 4 sample topics with top 5 keywords per topic. And from this, we demonstrated 33, 28, 25x speed for ANLS, PG, and PDC on 48 cores. So essentially, for the ANLS algorithm, this took around from 3 hours down to 5 minutes, from 1 core to 48 cores. Now let's quickly go over how one might go at extracting useful information from the factors once we've computed the factorization. So here we have our problem size, and here we have the top 5 keywords from 4 sample topics. So the way that you can arrive at these topics is basically you take a column of the W matrix, and then take, let's say, the top 5 values in the column W, which correspond to the top 5 words in the corresponding topic. Yeah, and then similarly, the columns of H might be interpreted as weighted topic membership of each paper to let's say a series of topics. So yeah, in summary, we did JointNMF solves the following problem formulation. It is an efficient interval method for analyzing high-dimensional data sets with symmetry constraints. And any attributed graph data set can be posed as a JointNMF problem. So social notes is done for generators and many more. This works presents the first attributed memory algorithm for JointNMF. We demonstrated efficient scalability to hundreds of cores. We then demonstrated indigenous effectiveness on a large group of data set. And finally, please see and be able for the important depth shuffling the trade-offs of the algorithms, and all the code and data sets are publicly available at the following GitHub link. Thank you.
So we have time for 1 or 2 questions.
This seems like something that would be useful as part of larger workflows. I've done work with building citation networks with Microsoft Academic Graph and Web of Science. Is there something like a science gateway or something where you can actually apply this algorithm on some of these large data sets? Because it's not easy for a lot of users to directly some of these data sets.
Yeah, so actually, we're actually currently, over the past couple months, we met with several researchers from the University of Michigan or Minnesota who are informatics researchers who are using NMF algorithms implemented within Planck to analyze their data sets. And actually, they're currently in the process of making with Python and R bindings for Planck, which should make it more readily available to users.
So I have a question. So if you go to the convergence slide, you'll find that the PG and CG converges very quickly. So is it possible, and one of them which converges, the ANLS converges very slowly. Is it possible to use PG and CG as, let's say, a preconditioner? So, and like it reduces the residual very quickly, and then use ANLS.
Yeah, that I think would be a valid approach. We haven't tried it yet, but that's definitely something we do. And one would expect that.
All right. So let's have an answer speaker.